see if there's something, if there's some other problems. Those ones, let's see, what is, oh yeah, there's a section here that all is explaining, you can prove that what they mean by reduced to echelon form is unique. You can show that that it's not possible, but that's a little bit complicated to say what's going on. Oh, the whole point of this is what the Gauss's method does. What Gauss's method, the whole idea is to isolate variables, right? In other words, you want, like, here's an echelon form matrix, and I've made it so that X is a leading variable and appears in no other equations. Y is free, and then this one here, XYZ appears only in this equation, and so it only appears in equations above it. So then when I do reduced row echelon form, each leading variable will only appear in its own equation. So what it's doing is it's Gauss's method works by eliminating variables from other equations so that there's no intertangling, so the equations are independent of each other. And it's like echelon form row independence. And this idea of independence is going to be formalized later as a central concept in linear algebra. So there's something like Gauss's method that's taking advantage of something about disentangling variables from different rows. And that's what it's trying to do. Okay, so let's so here's an example. These matrices are not row equivalent because their reduced to echelon forms are different. Let's see. Oh, yes, okay, so here. Let's do this problem on, not that, I want this. Okay. What I want, this is on page 133, problem 23A. Are these two matrices row equivalent? 1, 2, 4, 8, 0, 1, 1, 2. Are those row equivalent? You proceed by reducing each one to reduced row echelon form and seeing if they're the same or not. So see if you can answer this question, just as practice. You have an answer, okay. Okay, but a couple of people.